Okay, so optimization kind of has that word problem feel to it. It's similar to related rates in that way. That kind of feels like that kind of real world application. But the big picture is that really we're just trying to find a critical point. So if we can somehow set the derivative equal to 0, then that's basically it. If I can somehow get the derivative equation to show up, or get the equation to show up with one variable, set the derivative equal to 0, and once you can get that critical point, then your answer is just going to circle around that number. So, but the tough part is trying to get it down to that one equation where you can find the derivative. But once you get there, then it really is just finding a critical point. So optimization is a process of finding the greatest or the maximum optimal solution, or the minimum optimal solution. We don't have to worry about whether, if it's asking for maximum, that we accidentally find the minimum. Basically, whatever you find as a critical point, that's going to be your answer. So you don't have to worry about, wait, is that maximum, is that minimum? Basically, just whatever is optimal. The problem is always going to set up in a way where if you can find that critical point, that's going to be where your answer is. Which must be true regardless of solution. Optimization finds the most suitable value for a function within a given domain. So here are the steps, and then we can look at a variety of different problems. The first thing is we want to write the equation for the variable you want to optimize. The problem will be clear in terms of giving you context clues to tell you what variable to or what equation to optimize for. If it's asking, is it asking for the maximum volume? Is it asking for the minimum surface area? So the problem will tell you whatever to optimize, maximize, or minimize. Right? That's the equation that you want to find the derivative for. But a lot of times that equation is in terms of two variables, and we have to get it down to one variable. So we have to use a second equation to make the substitution into that first equation, that primary equation. And then from there, we find the derivative, set the derivative equal to 0, and then we solve. Okay, so let's look at example 1. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. Okay. What dimensions will produce a box with maximum volume? Okay, so here's the keyword here, maximum volume. We're trying to optimize volume. So let's build our volume equation here. Okay. So volume of a three-dimensional object is just going to be what? Length times width times height. Yeah, so 3 dimensions, right? So a box, find the length, find the width, find the height, multiply those together. So we have x, and h. Right? We have a square base, so we know the dimensions for the length and the width will be the same. So we can say x squared. But there's no relationship with the height compared to the base. So we have to use a different variable. So h. All right, so we're trying to optimize volume. That's the equation we want to find the derivative for. I'll put a star next to it because we have to come back to that and ultimately do the calculus with this equation. But we have a help equation, and that help equation comes in the form of surface area. So surface area is equal to, we're going to have to be able to build the surface area formula on our own. Okay, same with the volume. Okay, so the way we build surface area, it's exactly what the name suggests. We're going to add all the areas of each of the surfaces. Okay, so how many surfaces are there? How many sides are we dealing with? Normally it'd be 6, but there's something that tells us. What do you notice about this box? It's an open box, so therefore what? Yeah, there's only 5 sides that there's material for. Okay, so that open box, the top, we don't have to worry about anything covering it. So there's only 5 sides. So we're going to build the area of each of the surfaces of the 5 sides. Let me start off with the base here. What is the area of that base? X squared. Okay, so start off with that, x squared. Okay. All right, we have 4 more surfaces to worry about, right? So let's talk about one. Let's do the front-facing one. What's the area of this front-facing vertical side? X times what? H. Okay, so that's one of the sides. What about the back one? The one that's on the opposite side of the front one? Mm-hmm. What's the back side as well? XH. All right. What about the vertical side here? Also what? X times H. Okay. And then finally, there's another vertical side, and this last side is what? XH. Yeah. So as you build it, you're not going to try to memorize it because every base and width may have a different relationship, but we just have to understand, okay, how many surfaces are there? There are 5 surfaces. I'm just multiplying the area of each of those rectangles or squares, and I'm adding them up. So this is the area of the first side, second side, third side, fourth side, fifth side. Okay. So that's going to clean up to be S equals X squared plus what? Combine like terms. How many XHs do we have? Yeah, 4XH. Okay. Okay. They do give us surface area values, so we can replace S with 108. So this is the help equation. We want to use the help equation to get our volume down to one variable so that we can actually do the derivative. Okay, so this is the secondary equation that is going to serve the primary equation. Okay, so if we look, sometimes we can replace either variable and that could work. But I think in this instance, it's going to be only one variable that will be easy to replace. So what can we replace or how can we use the secondary equation to help us get the volume down to one variable? Which variable will be the easier one to replace? Okay, so if I try to solve for x squared, I will get 108 minus 4xh. And if I do that, I still have h and x left in my volume equation. So I have to get it down to one. I mean, it would be nice if that x squared, if that x wasn't here, then we can do 108 minus 4h, and that'll be fine. But in this case, if we solve for x squared, we're still going to have x left in our equation. Okay, so we only want one variable that remains. So what's our other option? H. Okay, so if I solve for h, I can get my equation in terms of x. I can replace h in terms of x. So my whole goal is, can I get my primary equation down to one variable on the right side? Sometimes it's interchangeable in terms of which one you replace. So sometimes you're forced into just going down one path because the other path is not going to work out. So let's solve for h. And I'm going to replace h as well. Okay. All right, to solve for h, I'm going to divide both sides by 4x. So now this is my substitution for h. I can replace that h in terms of x, and then I can get my volume equation down in terms of x, and now I can think about how to get my derivative to work out. So our volume equation is down to one variable. That's our first step. Our second step is how can we get it to the point where we can find the derivative? We shouldn't have to do anything more than power rule for these problems. I know this looks complicated. Maybe it looks like something you got to do product and chain and quotient. But notice there's only one term in the denominator. There's no messy exponent outside the fraction. I can just distribute the x squared through, separate each of the fractions, and just get it ready for power rule. There's no need to do anything more than power rule, but it does require a little bit of cleanup. So I'll distribute the x squared through. And I'm also going to begin separating into individual fractions. We can do this simply because there's only one term in the denominator. If there were multiple terms below, if it was like 4x plus 1, then we're kind of stuck having to go through maybe quotient rule. But here we can avoid quotient rule since there's only a singular term below. Right, let's keep cleaning up volume. I can cancel out one of the x's. I can divide 108 by 4x by 4. So this gives me 27x minus x cubed over 4. I can push that 1/4 out, 4 as 1/4. And that just makes it cleaner, I feel, in terms of thinking about power rule. We don't have to stare at a number of a denominator below a variable. I can just have that fraction in front. So once we get our primary equation down to a suitable place where we can find the derivative, we can just find the derivative, set equal to 0, and our answer is going to be waiting for us there. Okay, so v prime, 27x becomes what? 27. Okay, what's the derivative of 1/4 x cubed? Go through power rule, what do we get? Minus 3/4, yeah, x squared, okay. And once we have our derivative, we're going to set equal to 0. Yeah, we're always going to find the critical point. And now we're just off to try to go through our algebraic steps to solve for x. Dividing by 3/4, the same thing as multiplying by 4/3 on the other side. You can enter this in the calculator, or you can work this out by hand. 27 divided by 3 is 9. 9 times 4 is 36. So x is equal to 6. Okay, so given the fact that we have this much material to work with, our maximum volume will have a dimension of a base length being 6. Now, once you solve for x, you have to go back to the problem and figure out what the problem is asking for. Once you solve for x, you're not creating any more new content. You're just plugging into whatever the problem is asking for. Sometimes it's asking you for the maximum volume. Sometimes it's asking you about the dimensions. So whatever is needed, go back and read the problem. Everything that you need, it will be waiting for you to plug in. You're not going to create any more new formula. You're just plugging in to find whatever the problem is asking for. It's asking for dimensions. So dimensions is asking for the length, width, and height. We already have the base and the width. We just need the height. Do we have a formula for the height? Yeah, we got this one, right? 108 minus x squared over 4x. And we plug that in. That'll give us 3. And so our dimension, length, width, and height is 6 inches by 6 inches by 3 inches. All right, let's go to the next page. Okay, a rancher has 200 feet of fencing with which to enclose two adjacent rectangular regions. What dimension should be used so that the enclosed area will be at a maximum? So we see the word maximum is describing area. So we know that we have to optimize area. Let me draw this to the side and just label the x's and y's. So I have y's on this side, I have x's here. So I'll put a star next to area since that's what we're ultimately trying to get ready to find the derivative for. What is the area of this region here? Okay. What about if I ask just for the entire region? What's the close? Yeah, 2x times y, right? So the length of this is x plus x. The length of that is y, so 2x times y. Okay, so area is 2x times y. We do want to find the derivative, but we need some help because there's too many variables on the right side. So we have to get it either down to x or y. In this case, it doesn't really matter as long as we pick one to do. So the help is going to come from the perimeter. So the perimeter is telling us how many feet of fencing is involved to build this setup. So the perimeter. Okay, so if I add up all the lengths of fence that's required, what's um, what's the sum of all the sides? Okay, 200. What about in terms of the variables here? We can, yeah, set 200 equal to what? Yeah, 4x plus 3y, right? If I add up all those sides, I have 4x's and I have 3y's. Okay, so we do have a distinct amount of fencing that we're able to use. So this one is a problem where it doesn't really matter if you solve for x or y. They're both doable. They're both relatively about the same difficulty. I'm going to solve for y so that I can get my equation in terms of x. I just prefer x's if possible, but you can do the other way and you'll end up solving for y instead of x ultimately. But I'm going to replace y. So I want to find a replacement for y here. So 200 minus 4x equals 3y. Right, divide both sides by 3. Okay. So most of our work is just always trying to identify the primary equation that you're trying to find the derivative for. A lot of times that equation will have a second variable that we don't want to involve. So a secondary equation is going to help us get our primary equation down to one variable. And then once we're down to one variable, then we're looking to see how can I use derivative. Usually it's going to be power rule to help us get to our critical point. Again, this looks complicated with parentheses and fractions, but we can just rely on power rule. Okay? If we do enough cleanup, then it should be a relatively easy power rule problem. Okay, no need to go through quotient rule. If we just split each of the fractions up. I like to pull coefficients out in front of the variables, so it doesn't seem as daunting in terms of the derivative process. I would much prefer looking at this equation and this equation. They're the same thing, but visually it just feels easier because it just feels like, oh, it's just power rule with some coefficient in front. Right? We're going to find a prime, find the derivative, and set equal to 0. Dividing by 16/3, the same thing as multiplying by the reciprocal, 3/16. Threes cancel out. 400 over 16 is just equal to 25. So once we solve for x, we just go back and see, okay, what's the problem asking for? Is it asking for the perimeter? Is it asking for the area? Is it asking for the dimensions? But once you have your x, then make sure you go back and, I mean, you're pretty much near your answer. You just have to figure out what they're asking. Oh, they're asking for the dimensions. So I have x. I just need to figure out what y is. So I have a y equation waiting for me. Let's go ahead and plug that in. So if I solve for y, I get 100 over 3. So you can say 25 by 100 over 3. Or if we want to think of this as the full length here, you can also say, oh, it's 50 feet by 100 over 3. But either is fine. Okay. Next page. Okay, number one. So this is also area and perimeter, but now we're factoring in cost. So there's going to be cost associated with the perimeter. But let's build this shape first here. We got a rectangular field that's fenced off along the bank of a river. And we're not going to have any fencing needed along the side of the river. If the material for the fence costs $8 per foot for the two ends and $12 per foot for the side parallel to the river, find the dimensions for the field of the largest possible area. So this is telling us what we're trying to optimize area. That can be enclosed with $3,600 worth of fence. And this is going to be related to perimeter. We basically are going to multiply the cost into the perimeter equation, and that'll produce our cost equation. Okay, So I'm going to use X for my horizontal side, and then for my vertical side, I'll call them Y. The one that's parallel is going to parallel to the river is going to be the one that's more expensive, $12, and it's going to be $8 per foot per feet. So if I multiply this together, this will give me the cost, right? Because however long this is going to end up multiplied by $8 per foot, and that's going to give me the cost of this side. So what's my primary equation though? Area is equal to what? That's where we want to find the area. We want to find the derivative for, because we're trying to optimize area. Area equals what? What's the area of this field? Just XY, right? So the cost is not part of the area because we're not paying for the space inside. What's costing money is the perimeter, not the area. Okay. So the perimeter or the cost if I add up all this together, what will I get? Okay, X plus 2Y, but I want to involve the amount into the side lengths. So this will be what? 12X, okay. Plus 16Y, right? 8Y plus 8Y, 16Y. And how much money do we have to work with? How much is in our budget? Yeah, 30,600. Okay, so that will be here. Okay, so this is going to be our secondary equation. This is going to be the one that's going to support the area equation. Does it matter which variable that we solve for? I mean, they're both equally, in terms of difficulty, they're about the same. But I'm just always going to try to, if they're about the same, I'm always going to try to work towards X. I just feel X just feels more familiar. So to solve for, if I want, in terms of X, that means I got to get rid of Y. If I want to get rid of Y, I need to solve for Y. Divide both sides by 16. Make our substitution. So this will go in for the Y. And again, it looks complicated, but all we need is power rule to eventually find the derivative. See how far I can get from here. Once I have my area equation all nicely cleaned up and set up for power rule, I can set my derivative equal to 0. So I get x equals 150. It's asking for the dimension for the field of the largest possible area. It's asking for dimensions. So if I have x, I should need to find y. I have an equation that can represent y. So once you solve for x, we shouldn't have to create any more new equations. Just go searching in your problem to figure out any other variable that you want to solve for. So y is 3,600 minus 12 times 150 all over 16. Plug that in. We should get 112.5 feet. All right, number 2. So number 2, we're also, it's like the first problem where we're dealing with surface area and volume, but we're going to be factoring in the cost into one of the equations. So we have a rectangular storage container. With an open top. So again, there's only 5 sides to worry about. Volume of 10 cubic meters. The length of its base is twice its length. Material for the base costs $10 per square meters. Material for the size costs $6 per square meters. Find the cost of material for the cheapest container. We're trying to find the cheapest cost. And the cost is associated with surface area. So we're trying to find the minimal surface area, basically, which will, and then volume is going to be our supporting equation. Right. So I'm going to use a separate sheet of paper here so I can have enough room. Okay, so I have length of its base is twice as its width. Sorry, length of the base is twice as width. So that means if I have one side being x, I could have the other base length being what? 2x. And they don't tell us any relationship between the height and the bases, so we have to use a different variable. You can use y. I'm going to use h for height. Okay, so let's see. Volume is our supporting equation here. So volume is width times length times height, 2x squared h. I do have a set volume to play with here. I have 10 cubic meters. Now, ultimately, we're trying to minimize surface area. So let's build the surface area. And then once we build the surface area, we can factor in the cost of each of the sides. So let's build a surface area. So how many sides are we going to have to account for? 5 or 6? 5, yeah, open box, right? If it's a closed box, then we'll have 6 sides. But here, we don't have to pay for anything at the to cover the box, so only 5 sides. That has material. Okay, let's start with the base here. What's the area of the base? What's the area of that rectangular base? 2x squared, okay. What about this larger side here, this front side here? What's the area of this side? 2xh, okay. Do we have another side that has an area of 2xh? Yeah, behind it, right? So behind it, so there's another 2xh. What about the smaller one here? This one on the side. What's the area of that side? XH, okay. And then on the opposite side, there's another XH, right? So we're going to add up the area of each of the surfaces. There are 5 surfaces. Okay. Good so far? Now, there's costs associated with each of the sides, right? Or it says the base is the more expensive cost. The base is $10 per square meters, but the size is $6 per square meter. So we have to multiply $10 into the base, and then we have to multiply $6 into the cost of the sides. So I'm going to update the surface area equation and call it cost now that we have dollar amounts built in. So 20x squared plus, this is 4, 5, 6. This is 6xh times 6. So I get 36x h. Okay, I'll put a star next to cost because we're trying to optimize cost. We're trying to find the minimum cost given this supporting secondary equation. So which variable should we try to replace? H, yeah. So I'm going to replace h, and over here I'm going to solve for h. Reduce this, make it 5 over x squared if you want. And I'll take this, plug it into my h. So once I get my cost equation down to one variable, I can get it ready for power roll, find the derivative, set equal to 0, and solve for x. Okay, use your calculator. 36 times 5 is 180 divided by x. X and x squares canceled out. There's an x left below, but I'm going to bring it up to the top to get it ready for power roll. Okay, so once we get our primary equation down to one variable, we want to get it ready for power roll, then find the derivative, set equal to 0, and solve for x. I can set the two fractions equal to each other, cross multiply. See if I can solve for x. Okay, so once we solve for x, we're basically near the end of the problem, but we always want to make sure we go back and reread the problem and make sure that what they're asking for. They're asking for the dimensions, are they asking for the base length, are they asking for the height, are they asking for the surface area, are they asking for the cost? So what does the problem tell us that we need to find? Find a what? What are we looking for? It's part of it. What does the problem say? Find the what? Cost, yeah. So we basically have to just find a cost equation. Again, once you solve for x, you shouldn't have to create any more equations. Do you see a cost equation that we can plug into and find? Yeah, there's multiple, right? You can use this one, this one, this one. You don't want to use C prime though. C prime is something else. So any of these four is fine, but we probably want to just plug into the one that we feel is the easiest one to plug into. So maybe this one here, 20x squared plus 180 over x. So they don't have to deal with multiple x's. So you don't have to deal with negative exponent. So if I just plug 1.65 into one of the cost equations, that's going to give me my optimal cost. So the cost given the side length is 1.65 meters, it's going to come out to be $163.54. Okay, I do want to walk through number 3 since you're going to need this type of problem you're going to see in the homework. So let me just show you how to set this one up. Right. So number 3 says a piece of cardboard measures 10 by 15 inches. So we got a piece of cardboard 10 by 15 inches. F-O-U-R. 4 equal squares are removed from the corners of all sides. So we're going to remove 4 corners. So it's going to end up looking like this. We're going to fold the flaps until it forms a open box. Now, it's 4 equal squares. We don't know exactly what they are, but we're going to find the optimal maximum volume. So we're going to have to cut out 4 equal sides. So let's say this started off with a length of 15, and this starts off as a length of 10. If I were to cut out equal sides, what is the 15 going to be represented by? This length is no longer 15. It's going to be what? 15 minus 2x. Yeah. And this side is now going to be what? 10 minus 2x. So if I want to find the volume of this box, it's length times width times height. If I fold the flap up, that's going to be my height. What's the height of my box? X, yeah. So the flap is going to be X length high. So once that flap folds up, that's going to be the height. So we have the height times the length times the width. This problem doesn't require a secondary equation because everything is down to one variable. We just have to FOIL this out, find the derivative, or using power rule. And then once we find v prime, then we can solve for x. Okay, so that's how you're going to approach that problem. Your homework is directly in your packet, which is on page 36, 5, 6, 7, 9, 12, 14. It's just these 2 pages, page 36 and 37. The keys on the website, you guys can check your answers. Monday, we'll start our test review. Okay? And I'll hand back your quizzes as well. All right, come get your phones.